Hello and welcome again to my physics online video lecture series. Today's video we're going to be talking about magnetic fields and solenoids and toroids. This video is basically an application of the Ampere's law to these systems essentially. What exactly is a toroid or a solenoid anyway? Basically, a toroid has a geometry in which you have a wire that has many windings like this. And so there's winding upon winding upon winding upon winding upon winding. And then eventually there's an out for all these windings. And so each one of these sort of like loops here can be called a loop or a winding or a turn. So turn is a valid way of saying it, or winding, loop, any of that. Although maybe the caution with loop is that we may hook this up into a circuit, and so you have your circuit loop as well. And so if I was going to run current through the wire, like if I had current coming in one side and therefore coming out the other side, and this current would run round and round and round and round each one of these little loops. Okay, so now what we do is we kind of like look at this in cross section. So like if I took something and sort of like, here's my solenoid, chop the thing in half, what's going to happen? Basically an end-on view of each of these windings might look like this. And so each one of these would represent one turn or one coil or whatever you want to call out, one winding. And then as it winds round, you have the other coil or turn or winding or whatever you're going to call them. Okay, and so this whole thing basically ends up looking kind of like this in perspective. And then eventually you have like the wire out and the wire in. So if I'm going to draw the current for this, like let's say that the current is such that the current is coming out of the page towards us for each of these top parts, and then for each of these bottom parts the current would therefore be kind of going back into the screen or page. Okay, so I'm basically just drawing current as having some direction here. Looked at from the side, like if I were to take this whole thing and kind of like rotate it this way, these windings would basically just be stacked like this a bunch of times. And I've kind of like chopped it so that I'm looking at essentially like this side or this piece of the coil or of the turns, and so I've got like multiple windings of these, and so my current basically is just rolling around like this. And so this part right here, the top part, if we turn back around, we've got current coming towards us. The bottom part, we got current going away. We still have the other half. We're looking at a cross-section view of it. All right. So that's one thing to be aware of. Now, the question is, what kind of magnetic field is this current producing? And so to answer that, we want to use Ampere's law. And I guess I'll use maybe like green to represent my Amperian loop. Here's some possible Amperian loops. So I could like choose a loop up here, for example, entirely outside of the solenoid. I could also similarly choose one down here somewhere, for example. Okay, so these would both be valid Amperian loops. Both of them actually are going to give the same result. This loop has I enclosed equals 0. And the significance of that is that recall that Ampere's law says that if I were to sum around the loop for a closed loop, B dot delta L is equal to mu naught times I enclosed. The fact that I enclosed is 0 here for any arbitrary loop that does not go into or go through the solenoid. Any arbitrary loop out here or down here is going to have this result. It kind of implies that the magnetic field outside of the loop, so we could call that B outside, is 0. And this is since I enclosed is 0. Okay, so now the next thing that we can do is pick another one of these. We'll make it like this. So it goes part of the way into the solenoid, and it goes part of the way out of the solenoid. All right. So now we again apply the Ampere's law. Sum of the B dot delta L is equal to the mu naught times the I enclosed. Now out here we've already established there's no magnetic field. So that essentially means we're looking at magnetic field dotted with the little section of this and this that are poking in, and the magnetic field dotted with this line here. Now a magnetic field that is has a component not parallel to this side and to this side will nevertheless, unless it's like a really variable field, will nevertheless cancel for these two sides, simply because if I have a uniform field of some sort, this side right here, maybe the delta L vector is pointing downward, and this side right here, the delta L vector is pointing upward. So this would be like delta L for side 1, and that would be pointing in this way. For side 2, maybe it's this way. For side 3, it's this way. For side 4, it's this way. We're just adding up our delta L's as we go around the rectangle, all right? So now what I'm going to do is I'm going to kind of blow this thing up a little bit so that we can see it in detail. Outside of the solenoid, we basically have 0 magnetic field, and so the dot product B dot delta L4 is 0. And likewise, like this part and this part aren't going to contribute anything to their dot products. You could maybe look at like this portion of the line, this portion of the line. To get the field inside, what you essentially do, one way is you consider what the field from each individual wire is doing, and then kind of do like an envelope for the two wires. So let's take this down here. Essentially, like if you go really close to a wire, the magnetic field should look kind of sort of similar to what you would expect the field to be for a long straight wire, for example. And so, you know, this right here would be this wire's long straight magnetic field. This would be like the long straight magnetic field for this wire. And total magnetic field is, well, you just add the two together as vectors. And so you end up getting a magnetic field for this pair of wires that more or less looks like this. And so now, like, what would happen if we added a few more such of these loops together? Well, locally, you might have something that's starting to look kind of like this. So I'm going to just draw them close, but not like right, let's say on top of each other. And then this time I'll draw the current going in, since we're kind of focused on that part down here. Individually, our magnetic fields basically are doing this. Essentially, they're just kind of like looping around each one of these wires very close to the wire. So these represent like equa field lines, if you will. And so for, in between each one of them, I have one field going this way and one field going that way. And if I add the two together, I just don't have any field there. And then at the tops and at the bottoms, I effectively have a field kind of like this and a field kind of like this as my envelope. And so the total field very nearby, I would expect more or less to look like this. And then out here, maybe it goes down and then kind of more or less like this. Okay, so that's my total magnetic field. And you can imagine, like, we've gone from this to this. You can imagine if I have more and more of them and they're closer and closer spaced, there's more and more of like a ripple, but the ripple is smaller and smaller until the field starts to look more or less uniform above and below. Now, with that said, if I come back up here and look at these ones right here all basically have a field that above them should be pointing this way, should be pointing essentially to this direction. Below them should be pointing like this. These ones right here, above them have a field like this. Below them have a field like this. So now notice that this right here and this right here are opposite directions. So if you are below both, you have opposite that should cancel. If you're above both, you have opposite that should cancel. If you're in between both, they should add. And I can kind of like redraw this a little bit for emphasis, like for these lines right here. In this region, I'm above the lower ones, so I have a field pointing this way. I'm below the upper ones, so again, I have a field pointing this way. That means a net field pointing in that direction. Below here, I have a field pointing to the left from one and to the right from the other. And up here, I have one pointing to the right from one and to the left from the other. So if I kind of like color code my fields for these two, maybe up here, field is pointing in this direction above, field is pointing that direction below. For these guys down here, again, field is pointing in this direction above, that direction below, because current is in opposite directions. And so if I was to look in each region at what these fields are doing, in this region, the above is above this one, so the purple is kind of this way. The light blue also kind of this way. So we expect the field to just point, well, in that direction. So I expect like the net field to be this way. So we could call this B net. And then for the down here, I have a purple pointing to the left and a light blue pointing to the right. So I basically have a field that looks like this. So net field is 0. Well, we already knew that. And up here, what I end up getting is a field that points this way from the top set, and a field that points this way from the bottom set. And so again, that's a total field of 0. So if I put this in terms of total field, B equals 0, B non-zero, B 0. So what does my actual field look like then based on this drawing? Well, essentially it's going to look something like this. So my net field inside the inductor points, in this case, to the right. Outside, it's basically 0. Okay, so now let's take that and do the dot product with each of these sides. Essentially, delta L1 is perpendicular to B, and delta L2 is also, and delta L3 is also perpendicular to B. So that implies that B dot delta L1 is 0, and B dot delta L3 is 0. We already established that B dot delta L4 is 0. So that means that my total sum going around this loop of B dot delta L just ends up being B dot delta L2, and those two are parallel. B parallels delta L2, and so my total sum going around is B dot delta Li is equal to just simply B delta L2. With one little caveat, which is that my arrows for the B field are pointing to the right, and my arrow for L2 is pointing to the left, so they actually get a negative sign here. They're pointing in opposite directions, in other words. Okay. Ampere's law says that that should be equal to the total current enclosed. So Ampere's law now says negative B delta L2 is equal to, and now we ask, like, how much current is enclosed? Well, there's I running through the wire, so I can count how many wires are enclosed in this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 wires. And so I'd say something like 21 times mu naught times I. But again, this was kind of an arbitrary choice of L, so it might be more fair to say that what I have is mu naught times N enclosed times I, where N enclosed is number of turns inside Ampere loop, or Amperian loop, or whatever you want to call it. Okay. All right, I'm going to condense my loop a little bit to give myself a little more space to write down here, but basically Ampere's law, as written at this point, would say B times delta L2 is equal to negative mu naught N enclosed I. And where that negative is coming from, again, is that when you look at these, all of the current is going into the page rather than coming out of the page, and so we just kind of take that conventionally as like a negative current. If we draw the loop up here, then we would have a positive current, but also we would be on the part of the loop with my choice of directions, where rather than going one way, it would kind of go the other way. And so we'd have positives on both sides. The point being that I can now divide both sides by delta L2. And so B is now mu naught times N enclosed divided by delta L2 times I. And N enclosed was itself determined by essentially how long I've made my loop. Like, the longer my loop is, the more turns I'm going to be enclosing. Put differently, let's define a new parameter. Let N be defined by the total number of turns of my solenoid divided by the total length of the solenoid. It follows that the number enclosed would represent little n times delta L2. And so basically what this means is that B, the magnetic field, is equal to mu naught times number times per unit length times delta L2 times current divided by delta L2. And so my delta L2's cancel, and I'm left with B equals mu naught little n I. Or if you prefer, B is equal to mu naught total turns divided by length times I. But usually it's the top result that we specify for our solenoid. One last little thing then. This is supposed to be called solenoid and toroid. So you may be wondering, what does a toroid look like? The answer is a toroid basically is a solenoid that you've bent to make a donut shape. And so the sort of like relevant parameter here is what is the radius of the donut. And so this is like the radius to kind of the middle area of these loops. It turns out that the magnetic field for the toroid looks the same as for a solenoid, except for that we replace the L parameter with like a 2 pi r parameter. This results in a field which is confined to inside of the coils, and it's mu naught times number of turns times current divided by circumference, which is essentially the length.